Hello, everyone. Okay, now let's wrap up today's lecture by doing some sample calculations um, of calculating concentrations for H3O plus and OH minus. Okay, so say we have two pH values for two samples, lemon juice, pH 2.2, and vinegar, and they're quite similar. So they're quite similar, but we should calculate what the concentrations of each of these solutions are. Okay, so it might be helpful to know what the concentrations are. Okay, so first let's write the our equations we know for concentration. So we know that we can figure out concentration if we scroll back up here. That we want to use this. We want to use this equation right here. Okay, so we're going to put this in our calculator. So to do this, you're going to use the anti-log button, and the anti-log button is on your calculator like this, 10 to the power of x, and that's for log base 10. So logs are based on exponent of 10, or sorry, not exponent, but a coefficient, I guess, or factor of 10. Okay. So we know that for H3O concentration, equals 10 to the negative pH value. So we're going to take our negative pH value and raise it to the power of 10, like so. Okay. So we know our pHs. So for the lemon juice, we could say, so let's do our lemon juice here. Equals 10 to the negative 2.2. And if we carry out that calculation, we should get about, so since there's only one decimal point in our pH value, we should only carry out, we should actually only carry out this calculation to pretty much 1 sig fig, but we can carry it out to a little bit more here. So we're going to say 6.3 times 10 to the negative third molar. And we could probably just round this to 6.0, roughly 6.0 times 10 to the negative third molar here. Okay, do the sig figs. There's only one decimal place in the mantissa of the pH value, so we should only round. Oh, sorry, it shouldn't be 6.0. It should be 6. So we should only put one significant figure in the decimal place. Or sorry, one significant figure in our concentration. Okay. But let me just double check here because I just want to make sure I'm doing the right sig figs for logs. Okay. Okay. All right, let me see here. All right. I think that's how we do sig figs. So I don't think we have to worry about anything else. But let me just double check because there's so many rules for sig figs. Okay. Yeah. So basically, the number of sig figs in your answer, in your number, you're going to the sig figs in log is after the decimal point because The first number in the log just represents the magnitude of the value, and it has nothing to do with like the accuracy of the number. So the accuracy is actually after the decimal point. So in this case, there's only 1 sig fig, so we probably round it to 6 times 10 to the -3 molar. So we cannot really estimate the concentration to a very high degree. Okay, so that's lemon juice. So that's for H3O plus. So if we know H3O plus, we can figure out the OH minus, right? There's 2 ways we could do this. We can do pH. Oh, sorry, that's right over here. So we have room down there for the second problem. So we have pH plus pOH equals 14. So there's 2 ways you can do it. I'll show both ways. So if we have pOH, so we solve for pOH right here equals 14 minus 2.2, and that will give us minus 2.2, so that's going to be 11.8. Okay, so if we do the log now of 10 to the negative 11.8, we will get 1.6 times 10 to the negative I believe 11th, but let me double check here. So let me see, 10 raised to the negative 11.8. So yes, we get 1.6 times 10 to the negative 12. And we should probably round this to 2. Okay, like that. So you see here the concentration of the H3O plus is a lot higher than the OH minus, and that indicates that we have a very acidic solution. So it makes sense that lemon juice has a very acidic solution here. Okay, so here is the this will be H3O plus equals H3O. Oops, sorry, it's early. H3O plus, and then this value here, this will be our OH minus concentration. Okay, so there's another way we could do this. We can use the KW value, so we could say H3O plus times OH minus is equal to 1.0 times 10 to the negative 14th. Okay? So if we rearrange this equation, we'll get OH minus equals 1.0 times 10 to the negative 14 divided by H3O plus, which is equal to 1.0 times 10 to the negative 14th divided by the concentration here, 6.0 times 10 to the negative 3rd. Now we could do that. So 1.e to the negative 14th. Oops. Divided by 1e. Oh, sorry, 6e. 6e negative 3rd. And we get about the same number. We get 1.67 times 10 to the negative 12, but we're going to round that to 2.02 times 10 to the negative 12 molar. Okay, so there's 2 ways you could do it. So if you know H3O plus and you know the pH, you can use the pOH plus pH equals 14 equation, or if you know one of the concentrations, you can use the kW expression to solve for the OH concentration. Okay, so that's for lemon juice. Let's do let's do one more for now let's do for the vinegar solution. So that for lemon juice. Okay, so now let's erase this. So I'm just demonstrating that you use both methods here. They'll give you good approximations. So what I probably should have done is not rounded the concentration for lemon juice. So I probably should have kept the extra few digits if I'm going to use that value again for the kW expression. So I probably wouldn't have rounded this number here. I would have probably took this number out to a few extra digits, so it'll be more exact when I solve for OH minus using the kW expression. Okay, so that's just something to keep in mind. So vinegar. All right, so vinegar has a pH of about 2.5, so a little bit more acidic. So we could do H3O plus equals 10 to the negative pH, which equals 10 to the negative 2.5, which equals roughly 3.2 times 10 to the third. So in this case, we should probably, we would write 3.2. So let's just do it together. 3.2. So we get, so let's just give a few extra digits. 3.162 or 16 times 10 to the negative third. But you see here in our pH value, we only have one decimal point, so we should round to the first sig fig. So I'm going to underline here the 3. That's where I'm going to round my number. And so this will turn into 3 times 10 to the negative third molar. Okay. Now let's find the OH concentration. So the OH concentration, we will use the pOH equation. So pOH equals 14 minus 2.5, which is 11.5. Okay, so then OH minus would be equals 10 to the negative pOH. So this would equal 10 to the negative 11.5. And then we would bring our answer back down here, and we would get, so now let's now do 11.5. We get 3.16, identical answers pretty much, just different exponents. 3.16, underline here, times 10 to the negative 12 molar. So we would round this to 3 times 10 to the negative 12 molar. And now if we round these two numbers, we should get 14, or multiply 3 times 3e to the negative 12 times 3e to the negative third. Oh wait, yeah, so it actually does. Right, interesting. Yeah, so, oh, that's interesting. Okay. Let's see here. 3.16 e to the negative third times 3.16 e to the negative 12. Okay, so yeah, you do roughly get close to the kW value. Yeah. E to the negative 15. Right. Okay. And then you just move one decimal back. Yeah, so that's how you would do it. Okay, I was just double checking something mentally. So yeah, so that would be our answers there. Okay, so only one sig fig because there's only one decimal point after in the pH values. So we would use one sig fig in our answers here. Okay. All right, so that is how we do calculations using pH and pOH, and then solving for concentration. So very helpful information here. And then in the lab, we would take pH values and then use the anti-log. So use the anti-log equation to find concentration. All right, so now lastly, let's talk about the pH scale. So see here, this is how we would typically plot our data for the values of pH. So you see on this graph on the left, and graph A, that at neutral solution we would have equal concentrations of OH and OH minus and H3O plus. And then as we increase the basicity of the solution, as you increase the basicity here, it does go towards a more negative, more higher pH. And so we could plot all these concentrations here, as you see here, as you move either up or down, it'll get more basic or more acidic. Okay, so we all these pairs have a all these points here on this graph represent a pair of concentrations. So as you move to a more acidic solution, your basic your concentration of OH minus decreases, and as you move the opposite way, the concentration of H plus decreases as well. And then on the left here, we can plot this data to represent the relative concentrations of each, and it gives us a nice number scale to indicate, okay, we have something more acidic or more basic. Instead of referring to these concentration numbers, we can simply refer to a number scale that tells us how acidic or basic a solution is. So on table B here, we can fit these concentrations to this nice line, and if anything's above 7, we say that is going to be basic. So, and then anything that's less than 7 is going to be acidic. Okay, so let's see here as you do. When you think of pOH and pH, it's the measure of each ion. So the higher you go, right, the higher you go on the pOH scale, it indicates that you're going to be, you're going to have a less basic solution. And then on pH, so what we want to think about pH and pOH, the lower the number, the more the value for acid or base. So for pH, we're measuring H plus, so the lower the value, the more acidic. And then for pOH, we're measuring OH, so the lower the number, the more basic or more OH there are. So these terms might seem a little weird here, but you see as we go from 0 to 14, so these two graphs here, they're not really directly correlated. So you shouldn't match the highest point here to this point. That's not what you should do. Okay, so that has no relevance here. What is happening is you have you plot OH, and you see for acidic solutions, we're going to have pH is less than 7, and so as you go higher on the pOH scale, you're going to get more acidic, because your pH value is going to be higher, right? So or lower, sorry. So if we use the pKW expression, pOH was pH. The lower the number, the more acidic for pH, and the lower the number for pOH, the more basic it is. Okay. So pH, neutral solutions, pH equals pOH, and then acidic solutions, pH is less than 7, pOH is greater than 7. But for acidic, for our purposes, for the pH scale, we should just think of just pH. But pOH is also a measurement of how acidity as well, but it's more used for basicity. Okay, so it means basic, pH is greater than 7, pOH is less than 7. Okay. And now we have these lines here. As we see here, we can directly correlate concentrations with acidic, basic, and neutral solutions. So the pH of water is 7, so that's exactly a concentration of 1 times 10 to the negative 7 each for a proton and OH minus. And then as we kind of shift past that baseline here, so this is the baseline where it's all even. See, all even here. And then when we go, when we increase the OH concentration, the H plus concentration will now decrease, as we see here. And then if we go the other direction, we increase the H concentration, the OH concentration will decrease. So it's kind of a give and take relationship here. And then we can classify anything from 0 to 6 as acidic. So some examples of acidic solutions are bile, stomach acid, blood is partly acidic because of carbon dioxide. Cabbage juice is acidic, and vinegar, lemon juice, any citrus fruits. Basic solutions really have to do with like sodium hydroxide, the greaser. Solutions that are pretty much used in cleaning agents, I would say, but I can't really think of any natural examples where something is really basic. So in our cases, we will say a basic solution is probably anything that, bicarbonate. So like if you have sodium bicarbonate or baking soda, that is a basic solution. So it'll be around, I think it will be around like 7 or 8, but yeah, it will be a minor basic solution there. And then like sodium carbonate, pretty strong base, around probably like 10. So we'll be actually working with sodium carbonate in a future lab. Okay, so that is it for our chapter 4 solutions here. So next week we'll visit. Now we'll start talking about some other stuff. So we'll be talking about gases next. So the chemistry in the gas state, like how does that work? Okay, so we'll be doing a lot of discussion about the gas laws, ideal gas law, and then we'll talk about how we can use the gas law to solve a variety of problems referring to pressure, volume, temperature, amount of gas, and then we'll lastly try to come back and think about how gases, how the ideal gas law relates to real gases, and then we'll talk about kinetic molecular theory, and then we'll wrap up our gas talk with the Boltzmann distribution of temperatures, kinetic energy, speed of gas molecules and particles, and we'll introduce gas stoichiometry, where we use the ideal gas law and a chemical reaction to determine the amount of a product that may be produced from gas molecules. Okay, so that's it for chapter 4. I'll see you next time.